a simple pendulum, right? It's a rigid body, and the rotation is about a fixed axis, the point at which it is pinned to the wall. So I think would like to know is how to express inertia in that frame where it's not exactly passing the center of mass. So we'll see how those two things are applied when we solve problems related to rotation about fixed axis. Okay, so today's topic is rotation about a fixed axis. So I'm going to draw a random body, uh, create a pin joint at a point O. The center of mass is not at O, and then it's acted upon by a bunch of forces, all external forces and moments. So force F1, F2, F3, and say a moment M1. So when you have a rotation about fixed axis, it's generally recommended that you work with tangential normal coordinates for acceleration because equations actually simplify. Since this point G is spinning about point O, it's best to use AT, AN coordinates. So what we'll do is I'm going to draw the free body diagram. So when I draw the free body diagram, I'm supposed to remove the pin joint and replace the effect of the pin joint with a force. So let me get rid of this. And draw forces at the point O. So before I do that, let me choose the coordinate frame, which is going to be the normal and tangential coordinate frame. So this is the normal, this is the tangent, this is T, this is N, well if you like okay. So I'm going to put it at O because let's assume that's to be the origin. So you can choose the origin wherever you like, right? So most times it makes sense to put it at O. So I'm going to draw this right here, T, N, and put the forces at. So OT is the force in the tangential direction. ON is the force due to the pin joint in the normal direction. Okay, and let's say that this distance is RG. Okay, so I'm ready to write the equations. So again, there are three equations when you have a rigid body motion. There is F equals ma. Since I choose the coordinate frame which is tangential normal, I need to write Ft equals mass times acceleration in the tangential direction, which is equal to mass times. So the acceleration in the tangential direction is what? It's alpha times rg. So if you remember, it is if I believe it's written like this: theta double dot r, right? At, which is the same as alpha times rg. Alpha is the acceleration, angular acceleration. So angular Similarly, Fn equals MAN equals mass times the centripetal acceleration, so it's m omega square rg. Omega is angular speed. And then the last equation is the moment about point G, and that is Ig alpha. So unlike the previous section, right, the problem where the rigid body is translating, in this case alpha is not equal to 0. So the third equation is not, mg is not equal to 0. That's the only difference from the previous section.
So it will rotate about an arm.
It will rotate, yeah. So example would be a simple pendulum. So what will happen is when you try to use this equation, let me just put it in a box before I. So when you will use this equation, let's look at equation 3. Okay, equation 3 is saying the moment about point G is Ig alpha. Okay, Ig comes from that, we either give it to you or it's in the table. Alpha is usually given to you. Mg is the moment about point G. Okay, so when you find the moment about point G, it will be the contribution due to M1, F1, F2, F3, the external forces, and they are given to you. So, and you also given the point of application, so you can find the moment. But this mg will also include the effect of OT and OM, right? What's the moment due to OT and OM? If OM passes through G, it is 0, but OT doesn't pass through G, so it will be OT, assuming that RG is the normal distance, will be OT times RG. So this thing here on the left hand side will have all things which you know, the forces, and also have OT and ON coming in here. Right? Now most times you are going to find the acceleration. In order to find the acceleration, you have to basically know everything on the left hand side, but OT and ON is not given to you. So it becomes that so boils down to you using these two equations to find OT and ON, and then subbing in here to get alpha, and that is more work. Right? You have to think of just three equations here and solve it. So there's a simpler way. If you're trying to find the angular acceleration, do not have to use all three equations to get the acceleration. So the next step is another way of solving the same problem. And so if that was very unclear to you, don't worry, I'll solve a problem, it'll become clear to you. So there's another way to write the equations. This would be the first two equations remain as it is. Ft equals mass times At, which is m alpha rg. The second equation remains as it is, Man equals mass times omega square rg. However, the third equation is, instead of taking moments about point G, we take moments about point O. And the reason we take moments about point O, okay, point O is here, is that if we take moments about point O, then we do not have OT and ON coming into the expression, because OT and ON passes through O. So the moment at O due to forces at O is going to be 0. So we write MO equals IO alpha. Note that here I had IG alpha, right, because the moment was about point G, and now I have MO and IO alpha. That is, I need to find the inertia about point O and not about point G. And that's because we're taking moments about point O. So either you can use equations in this fashion, these three equations as a pair, as a set of three equations, or you could use these three equations to solve the problem. The advantage of set 3 of this set, second set, is that, as I said, the MO will not have the reaction forces. Okay, so that will become clear in a bit when I solve the problem. The only caveat now is that you have to find IO. IO is the inertia about point O using parallel axis theorem, right? In the first case, this case, IG, this is something I will give it to you, so you can directly sub in. So you do a little bit more work to find IG, but IO, but then you do not have to deal with the reaction forces. So IO is Ig plus mass times Rg square, assuming that Rg is the normal distance. So let me call this set as set 1. We call this 1. Let's call this 2. So is this the same thing which I wrote on earlier for particle motion? You draw the free body diagram, draw FBD, write the equations of motion. So use 1 or 2. And then finally, and this is optional, and it depends on the problem, use kinematics to solve for V or R. So V is velocity as a function of time, and R would be position as a function of time of G. So say Vg as a function of time, or G as a function of time. So usually the second step gives you solve for, it could either be the forces, reaction forces, and acceleration. So solve for reaction forces and linear and angular acceleration. So draw free body diagram, use equations of motion, and they used either to solve for reaction forces, that could be one of the things asked, but most certainly will ask you to find the linear and angular acceleration. So you find that, and once you know the linear and angular acceleration, you can solve for a Vg as a function of time. You could also solve for omega as a function of time, and theta. So omega is a scalar. So omega as a function of time, and theta as a function of time. Right? Omega is obtained by integrating angular acceleration. Theta is obtained by integrating the angular speed. And Vg and Rg can be obtained by integrating acceleration, the linear part of acceleration. So that's it. So given that, we will now try to see how we can apply this.
So I'm sorry, it's not good. I just said the question. What is RG again?
Rg is the position of center of mass as a function of time. So I did draw Rg here in this figure, but this Rg is just at that instant. But I'm more interested in finding Rg as a function of time. So as the acceleration changes, Rg will keep changing. Okay, any other questions? Okay, so uniform slender rod of mass m is released from rest when theta is 0. So it's released from this position. This is theta equals 0. Determine the magnitude of the reactive force exerted on it by pin B here when theta is 90. Yes. First, think about it. If you have a slender rod at 0 degrees and you let it go and it rotates, it cannot rotate by itself. It needs to be acted upon by an external force. So what is not shown here is that there is gravity. Without gravity, this slender rod is not going to rotate, right? Because there are no external forces, there is no gravity. So under gravity, it rotates. Okay? Clearly, it rotates the way I've shown because assuming that it's given to you, it's a uniform slender rod, which means that the center of mass is right in the middle. Right? Since the center of mass is right there, it's going to move clockwise. Okay, so let's start with the free body diagram. Okay, when you're drawing the free body diagram for something like this, when you're told to find theta at an instant, right? Theta at 90 degrees, you're going to find the reaction forces. I highly recommend drawing the free body diagram at an angle, not at 0 degrees or at 90 degrees, because what you have to do essentially is you need to eventually integrate. So writing it at a general angle is better than writing it at any of the extreme positions. You can always put theta equals 0 or 90 once you analyze the system at theta equals a random angle theta. So,
don't change your axis?
say that again?
Are you saying like don't change your axis?
No, what I'm saying is, one way you could have posed this problem in the exam is like I could have shown you at theta equals 0, right? Shown you this figure at theta equals 0. I could have shown you the figure at theta equals 90 and told you to do the same problem. I wouldn't have shown you at this particular orientation. What I'm trying to say is when you're drawing the free body diagram, instead of drawing it at 0 degrees or 90 degrees, these are the two important things here. I would recommend drawing the figure, the axis, or the rod at an angle theta, where theta is not 0 or 90 degrees, so that you can write the forces in the right way. Write the forces in this particular configuration. Don't draw the free body diagram in this or this configuration, because these forces are going to be a function of the angle theta. So if you draw it at 0 or 90, it will not give you how the forces change as theta changes. So this is sort of the right way to do it. It is draw it at that way. Because I found a common mistake last time when I taught it. People would draw the diagram at special angles. So since there's a pin joint and I'm interested in I want to use normal tangential coordinates. BT is normal to the slender rod and BN is normal, so 90 degrees. G is somewhere here, it's somewhere to the right. So that's vertical. And then if you want, you can draw the tangential here or here. Let me just write here. This is the coordinate frame. UT is like this. UN is always pointing towards the center of center point, right? About which it's rotating. This should be B. This should be. Okay. Is there any other external forces? Yeah. Question.
Yeah, just real quick. So in this problem, we were not given the center of mass. However, we always know that it's at the center, right?
No, you're actually given the center of mass in a very non-direct way. You're told that it's a uniform slender rod. The word uniform slender rod means that the mass is uniformly distributed. So the mass has to be the mass has to be center of mass has to be midway. But if you are not given this, you can assume it anywhere you want. If you put it right here, it's not going to move though. It's midway, so this has to be L divided by 2. And then this is again L divided by 2. So the drawing is not quite to scale, but it should be midway. Okay, so equations of motion. Okay, so there are three equations, two for forces, one for rotation. Let me write the equations for forces. So Ft is ma_t. So the net force is equal to mass times acceleration in the tangential direction. So this gives me the net force in the tangential direction is Bt. Bt is acting in the negative direction of ut, so it's negative Bt. Mg is, well, it's at an angle theta. So if this is theta, this should be 90 minus theta. So this angle here should be theta. Right? This is theta because this angle is 90 minus theta, and this angle is theta. So this angle is, let me just write it down, 90 minus theta. That's theta. So if I want to find the force due to mg in the tangential direction, I need to do mg cosine of theta. So when I do mg cosine of theta, this force acts in the ut direction, right? So it's positive, equals mass times the acceleration. So acceleration in the tangential normal frame is alpha times rg, where rg is the distance, is this distance. So this distance, what's that distance? It's L by 2 minus L by 3, yes. That's L by 6. It's L by 6. Okay, so I do not know what alpha is, it's an unknown, and I do not know what beta is. So that equation has two unknowns. Similarly, I can write Fn is m times an. So the force in the normal direction is Bn, and it's in the positive n direction. So plus Bn. Mg also has a contribution. So Mg sine of theta, right, is going to give me the contribution due to gravity. But Mg sine theta is going to be acting in this direction. So that's going to be negative to the normal direction. So that is equal to mass times omega square rg, which is equal to m omega square L divided by 6. So in that equation again we have two unknowns. Bn is an unknown, omega square is an unknown, or omega is an unknown. So we cannot solve for, that equation cannot be used to solve for any of those two.
Will you provide those
These equations, I've got to check the formula sheet. I believe not. What we would give you is, we would give you the acceleration in the normal, and we'll give you formulas for acceleration. You got to write those equations. These equations are problem specific. It's not like there is one formula which fits all. Yeah. You got to remember those three formulas, which is Newton's law, then Newton's law is for rotation. Okay, so Clearly that doesn't help us to solve the problem. We need to invoke the moment equation. Now, as I said, there are two ways to write the moment equation. One is you write the moment about point G, about point G. If you write the moment about point G, it's going to have Bt and Bn coming in the equation. In fact, it's not going to have, sorry, it's not going to have Bn because Bn is along G. Right? Yeah, it's only going to have Bt. And I'm not interested in Bt. Well, I'm interested in Bt, but what will happen is I'll have another equation for Bt and alpha. There will be three equations, three unknowns, and there's going to be more work. So in order to avoid that, instead of taking moments about G, I would recommend taking moments about point B, so that you will eliminate all forces at B in the equation. So what I'm going to do is I'm going to take moments about point B equals I about B times alpha. Okay, the moment about B, this point, as I said, will not have any contributions due to Bt and Bn. The only contribution will be due to Mg. Okay, so what's the contribution to Mg? So Mg, which is acting downwards, can be resolved into two ways, right? Mg cosine theta acting in Bt. You see Mg cosine theta acting in Bt direction. So that's moment Mg cosine theta, which is acting this fashion, is going to have a moment arm of, what's the moment arm? It's basically L divided by 6. Okay, and it's acting in the clockwise direction, right? If you hold B fixed and you apply the force mg, it's going to make the rod turn in the clockwise direction, so that's going to be negative. The other contribution is due to mg sine theta. Mg sine theta is acting this way. So mg sine theta passes through B, right? Line of action of mg is through B. So the moment arm is actually 0. So there's no contribution due to mg sine theta. The only contribution is mg cosine theta. That is equal to I about B. We need to find the inertia about point B. So inertia about point B is inertia about point G plus mass times the distance between B and G, which is L divided by 6 square times alpha. Now this is something which I'll give it to you. It's I think 1/12 ml square. This is given. Okay, so what you see here is in this equation, the nice thing about this equation is alpha is the only unknown. Everything else is known. I know theta, I know mg, I know everything. So you can simplify. You get alpha equals 3 divided by 2g sine theta divided by L. So let's call this 1, let's call this 2. So let's say simplify. Simplify 3. Okay, so if you now know what alpha is, we can now start solving for Bn and Bt. The question is, you're asked to find Bn and Bt, right, when theta is 90 degrees. So let's try to solve for Bt. So Bt equals, so from 1, Bt equals mg cosine theta minus m alpha L divided by 6 at theta is 90 degrees. So this gives me mg cosine theta minus m. Alpha is given, right? Alpha is 3 divided by 2 G sine theta divided by L, that comes from times L divided by 6. I think I did a yeah. Yeah, that's the problem. I wrote it wrong here. Think this is wrong. You're right. This is incorrect. This is cosine. Yeah, this is cosine. So it actually comes out to be this. So it's basically, so there's mg times cosine of theta, right? I need to find when theta is 90. Cosine of 90 is 0. So this term is 0. Cosine of 90 is 0. So it's actually 0. Vt is 0. Okay, next thing I need to find is Bn. Okay, the issue with finding Bn is I need to find omega. I don't know what omega is. I know what alpha is. So in order to find omega, I need to take alpha, integrate it once, find omega at theta equals 90, and then sub it in 2 to get Bn. So let's do kinematics. D omega dt is alpha. Alpha is 3 divided by 2 g cosine theta divided by L. So how can I integrate this? How can I integrate dw dt when on the right hand side I have theta? Okay, so what I have on the right side is a function of the position, right? When you have it as a function of position, what I recommend is not using d omega dt, but using the other formula, which is, right? This is the equivalent of v dv ds, because on what I have on the right hand side is a function of theta. So when I integrate this from 0 to omega, it starts with 0 angular speed. I need to go from 0 to pi by 2. What I get is omega equals 3g. So you got to go and check this if this works out right. This is what I got by when I do the integration. And then once you have this, now put 4 in 2 to solve for Bn. So Bn comes out to be, so please check this, mg sine theta plus m omega square L divided by 6. It works out to be 3 divided by 2 mg. I did not get the numeric value, but it's kind of obvious how to get the numeric value once you know in terms of mg. Okay, any questions? So the key thing is, yeah.
What they're even getting right now is just numeric.
Oh, it's just numeric? Okay, my bad. It has no numeric value in this problem, right? You're not given the mass and gravity. So the key was not to use the set 1, which was taking moments about point G, but taking moments about point B.